So let's continue. Please welcome Bill Stuart, Technical Staff Applications Engineer at Microchip Technology, with over 20 years of experience in embedded systems and automotive applications. Throughout his career, Bill has led the development of cutting-edge demos and training materials and secure communication technologies, including MACsec, MKA, Secure Bot, and CAN-based systems. He has presented at major automotive events across the globe, sharing deep technical insights and hands-on solutions for secure and connected vehicles. Today, he'll be walking us through Microchip's MKA and MACsec overview, offering a closer look at how these technologies are helping secure automotive Ethernet networks for the next generations of mobility.
Thank you for having me here. It's an honor to be here presenting Microchip's 10BC1S MACsec solutions. I'll be going over the next 25 minutes, details on MACsec and MKA. I won't be able to dig deep into everything because we just have 25 minutes, but hopefully we'll give you a good introduction of MACsec and MKA. So the agenda for today, we're going to have some brief intro into 10BC1S and security. Then I'll cover MACsec and MKA topics, and we'll have some key wrap-ups. 10BC1S is a 10 megabit multi-drop bus, so supported with unshielded twisted pair. It's similar to the CAN bus. Some people consider this to be a replacement for CAN bus because CAN FD has a smaller payload, slower speeds. It's similar in terms of the multi-drop. Every message on 10BC1S is accessible to be viewed by all other nodes, similar to CAN. So that was some security risk. So just a quick primer on security. These are some key principles for security. Authenticity. It ensures that data is received from a legitimate and a dedicated source. Data integrity ensures that data has not been modified in transmission. And confidentiality is the principle of ensuring that the information is only accessible by those that are authorized. So if you have a transmitter that's trying to transmit a message to the receiver, and they want to transmit an encrypted message, they'll encrypt that message with a symmetric key, and the receiver will be able to decrypt that message. And it's the key that proves that they are authorized. The good thing is MACsec provides all three of these core principles using AES, GC, and Cipher. I have a bunch of terminology slides in the back of this presentation. I'm not going to go through all of them, but this is the key one. So this is the keys that are in MKA and MACsec. So the first is the root key. It's called a connectivity association key. This key itself can be stored in the life of the module, or it can be changed out in MKA. The connectivity association key name is a label for that key, and both those together are used to derive the IC and the KEC. So we don't want to use the root key often, but it's just used to derive two more keys. So the IC is the integrity check key, and that's what's used during MKA to generate the integrity check value that's put into every MKA frame. And the KEC is used by the key server to key wrap the new session key, and then all the pairs that receive that key use AES to unwrap that key and use it to install it. So these keys are used in MKA. The next key I want to talk about is the secure association key. This is the essential testing key that's used in MACsec. And if you use MACsec without MKA, it's considered a pre-shared key, but with MKA, it's more like an ephemeral. You can update this every 2 seconds, every hour. It's really up to the key server. So we would store the CAC in long-term GL-high key storage, and the SEC would be session key, could be used in HSM or even the microcontrollers RAM. There's short-lived keys. So Microchip has created a 10BC1S MACsec MKA demonstrator based on a 2018 second edition of MACsec spec, so 802.1AE. The first edition came out in 2006, and then we also incorporated MKA into the demonstrator as well. It uses 10BC1S as the physical layer. subgroups that are working on taking MACsec and MKA and applying that to automotive. So automotive profiles being defined, how to use MKA and multi-drops being defined, as well as how to speed up MKA. Currently, the specs for MKA take two seconds, or in orders of seconds, and they're trying to speed it up in orders of milliseconds. And just for completeness, we have the NIST specifications listed here too. So we'll talk about MKA, MACsec now. So what is MACsec? MACsec is media access control security. This provides security from layer 2 and above. So we look at the OSI stack. MACsec is at layer 2, and everything above that is unaware that MACsec is being employed. MACsec can be done in hardware. It can also be done in software, as we show in today's TMS demo. And the reason why we were able to do it in software is because today's TMS is a slower physical layer, slower internet. So we also have highlighted here MACsec, IPsec, and TLS. Those are other protocols that are used to secure data packets. So TLS is really application specific if you're using HTTP or SMTP. IPsec is if you're trying to secure packets long distance, say from Petro to Detroit, Michigan. MACsec is used for the local area network, and there's low overhead for MACsec. MACsec protects all traffic above layer 2, but it can be used in conjunction with IPsec and TLS. So why is MACsec important? Multiple types of attacks can be applied to the Ethernet bus. One is a spoofing attack. So you can have a bad actor that's trying to transmit a valid Ethernet frame, trying to get the receiver to do something. And the good thing about MACsec is that every MACsec frame has a integrity check value that's in the payload. And so when the receiver receives the frame, it's going to check and see the ICD is valid. Integrity check value is valid. If it's not valid, then the receiver throws out that frame and it commits an error counter. So MACsec in this spec has a variety of counters that track bad frames, no tags, and such things like that. Another type of attack is a man-in-the-middle attack, where the attacker is going to receive a valid frame, maybe it's spliced in into this bus, receives a valid frame, and tries to modify slightly in the payload, and then retransmit that out. Well, that would also break the integrity check value. So you modify the payload, then the ICD, which is like the digest of the message, breaks. So the receiver will see that, not process it, but then increment its error counter. The passive attack sniffing is where the attacker is going to try and sniff the bus to learn something about the network. In MACsec, you have authenticated messages. You also have authenticated with option to encrypt data payload. So in that case, if you encrypt your payload for sensitive data, then the attacker will not be able to learn or glean much from the network. The final attack is a replay attack, where the attacker is going to sniff the bus for some time to capture valid messages, and then later attempt to replay them to disrupt the network. So an example would be maybe you're applying your brakes in your vehicle, the attacker is sniffing that messages on how to apply the brakes, and then later on when you're driving 100 km per hour on the highway, the attacker is going to attempt to replay those messages. And they're completely valid messages. The only problem is in the MACsec frame, there's a sec tag, it's a field inside the Ethernet packet. And in that field, there's a packet number. It's always incrementing. So if you attempt to replay old packets, the receiver is going to know those are old packets and will throw out those messages and increment error counters. MACsec does allow for a replay window, but if you don't want it to be open to a replay attack, you just set the replay window to 0. So if we look at the Ethernet frame, how does MACsec affect it? So first thing MACsec is going to do is it's going to add a MACsec sec tag in yellow. That sec tag contains the ether type for MACsec. So that's always going to be 88E5. And then it's going to also have a packet number in there. So I mentioned the packet number is always increasing. And the E and C bit, the encryption and change text bit are there as well. So the receiver will know whether or not that's an authenticated MACsec frame or it's an authenticated encrypted message. The encrypted message is different from the authenticated in fact that we are going to encrypt the payload. So we are also encrypting the original ether type as well. And this is about 32 bits of additional overhead. It could be small items. So the MACsec sec tag also includes the secure channel identifier from the transmitter. That's optional in point-to-point networks. So if you take a look at an example MACsec network, we have multiple nodes here. They've all been provisioned with various SCIs, so secure channel identifiers. They're unique for each node. They've been provisioned with a transmit key. And for all the nodes they're going to talk to, they've been provisioned with the receive key, essentially, that the transmitter is going to transmit with. So MACsec allows for each node to have one secure channel, and then additional, every node can have additional receive channels. So take a look at this. Node C has one secure channel that's able to transmit out on the 10^15 bus, and it would address the messages by changing the destination address. You are able to have another secure transmit channel, but you just have to have another secure channel identifier defining that node. If you take a closer look at the secure channel, there's also 4 secure associations. So in this example network, we've only tied the symmetric key to association number 0. So you have 3 additional keys. This is MACsec without MKA, so this is pre-shared keys. So let's take a look at how MKA affects and is used with MACsec. So MKA is the MACsec Key Agreement. It's used to generate keys and distribute them among the nodes in the network. It's defined in the Extensible Authentication Protocol, the IEEE spec, and in the demo we're using a section called MKA MKA. So this is a one-slide overview of MKA. So the Content Association is the group of members that want to participate in MKA. So they're all going to share the same group key, the CAC, and CKN, which is the label for the group key. And then with that CKN and the CAC, they're going to derive the DIC and the CAC we talked about earlier. So all the pairs will derive those keys themselves, and they can store them for use later on. The IC is used to create the integrity check value, the MKA packets, and the CAC is used to key wrap the session key and by the key server and distribute that to the peers. So once all the nodes have generated keys, they can start transmitting MKA packets onto the bus to announce to everybody else who they are and what they want to do with MACsec and MKA. And they all can also give information as whether they want to be a key server or not be a key server. So you can have multiple nodes that want to be a key server on the network. So that's some redundancy that's built into MKA. But there will only be one active key server, and that's based on the key server priority. So once they all transmit out who they are and all the nodes and all the pairs on the bus, there's no nodes that have not been sent out their information. And then the key server can now start to generate the session keys and distribute them among the nodes. So the key server will transmit out the session key wrapped. The nodes will unwrap that and install it. And they'll announce to the key server they installed the key. And once the key server sees that all the pairs have installed the key, then the key server will tell the nodes they can start transmitting with that session key. And that's the MKA sequence. And the next step can start at that point. So we take a look at the MKA frame. So we have our destination source address. The ether type for MKA is going to be 888E, triple E, and then we have the MKA data. So if you take a look at that data, there's a header field. So the E8 poll protocol version is 3, E8 MKA packet is 5, and then we have some parameter sets. In every single MKA frame, there's going to be a basic parameter set. So that's every other node information about the transmitting node. And then there's going to be an ICV indicator. So that's similar to that MACsec ICV. It's generated slightly differently. It's generated with AES-CMAC, but that protects the integrity of that MKA frame. And during the process of MKA, there's multiple steps. So there's multiple bits of information we need to transmit in this packet. So if we take a look at the other parameter list, like the live pair list or potential pair list, will get transmitted out in this packet. So we just add those to this payload. So at some point, we're going to transmit out the session key. The session keys are useful. There's a packet number that's at the sec tag, 32-bit value. If you were to transmit 100% bus loading at 128 frames, you would use up that 32-bit value within 9 days. So using up a simple loading for 90 days straight, but the point is that that packet number can reach a threshold. So you're going to want to rekey, and you don't want to take your vehicle to a service center, so you want to use something like MKA. So rekeying can occur for many reasons. So if there's a new member that joined the CA, so if there's a new module that's been plugged in, it's going to announce who it is to the rest of the bus, its capabilities. The key server will see this potential new node, and then we'll start to redo a MKA session to generate a new session key so that new node can participate in the MACsec traffic. And if the member's message number or packet number, MACsec packet number reaches a threshold, then you're going to also want to rekey. You never want to reach the maximum threshold of your MACsec key, otherwise you're going to be open to prevent attacks. So there's a 80% value of the MACsec key. At that point, you want to initiate a rekeying sequence. You could also rekey on a rekey timer. So on our demonstration unit, we can rekey every 2 seconds. And you can see the rekeying process on Wireshark or using the Vector tools. And you can see the rekeying process happen, and MACsec is happening at the same time. Because when rekeying happens, you don't just swap out the new key with the old key. There's a timer where both keys active. And you can also have the key server drop off. So that we mentioned there's redundancy built in, so you can have multiple nodes want to be a key server, one active key server. So if the active key server drops off, the other nodes will notice this because there's a liveliness on a live message being sent out with information. So if the other nodes see the key servers dropped off, then another node that wants to be a key server will try and promote itself. Take a look at the MACsec MKA 4 nodes we had before. We can see that every node's been provisioned with a CAC. So we typically put this in a chill high security storage. The IC and CAC have been derived. And then the key server here has already generated the SAC and installed that out to the nodes. So they're all going to install the SAC. And I have this little SAC 0, so it's installed on association number 0. And so at this point here, once the SAC's been installed, then MACsec traffic can start. At some point, you're going to want to rekey because maybe the packet numbers reach this threshold. So then the key server is going to generate and distribute a new key. So it's ASQ wrapped to these nodes. They're going to install it, let the key server know that they installed this new key. Then the key server let the nodes use it for transmitting. And that new key will be stored into the AN1 slot. And this will happen whenever there's a new key. So you can see I've always shown 2 keys listed because in the MKA packet there's a latest and an old key slot. The point is you want to have a make before break update. So you don't want to leave a node without the latest key. So when we in this situation here, we have this set of key that's been set up. They were using this key, and then a new key gets generated and distributed. This key is then only used for receiving. And then all the nodes should use this key for transmitting. And once all the nodes tell this key server they're using this key for transmitting, then all the nodes have to perform maintenance, and they have to remove that old key. So some key takeaways of MKA MACsec. First is MACsec can be leveraged for automotive industrial applications, multiple speed grades. So MACsec has already been out in the field since 2006. The second edition is 2018. So you'll see this in a lot of switches from varieties of vendors. Microchip has them as well. But 10BC1S is a new network for automotive. It's slower speed, so we can do MACsec in this in software. We recommend that you store the CAC, the root key, in GLI key storage. And then MACsec is the only solution that can protect all unicast, multicast, and broadcast traffic. And MACsec, in conjunction with MKA, can quickly change keys in the field, so you don't have to take your vehicle and be serviced. Finally, Vector provides the hardware and software tools to analyze run simulations and test Ethernet networks with MACsec. And this includes from 10BC1S all the way up to multi-gig. Update from Microchip. In 2015 March, there was a Ethernet conference in Munich. So Microchip participated in that technical review session, Plugfest. So we brought a few different 10BC1S nodes. We performed MACsec authentication encryption, ASGC on 128 and 256. We acted as a key server, worked with key servers. perform MACsec line rates, and we interact with other vendors who have 10-2 solutions. So we have a variety of products as well as endpoints for Microchip that support 10-2S, MACsec and MKA. And we also have our chill high security storage secure elements. This is an example of a node that we have on the booth now. It's a DS PIC. We have MAC5 parts, T100 for secure key storage. We use a simple tool for sniffing the bus, but we've also worked with the Vector VN5650. It's a multi-port switch, multiple 10-2S nodes connections here. So this setup is a very simple setup for 10-2S. You can get used to get up and running for proof of concepts. Last thing I want to mention is this is a quick 25-minute overview, but we have a 3-hour class that digs into VLANs and other topics as well, offered in Scottsdale, Arizona. Thank you so much. Any questions at all?
So how are the new keys generated? Are they generated on the fly, or is there like a maximum number of new keys that you can generate? How does it work?
So the key server itself
Yeah.
could use a true number generator to generate new keys. There could be a list that also has been stored in the key server as well to send out.
Okay, so is there a possibility then that you can run out of new keys?
No, if you generate it with a key server that has true number generator, you can constantly generate new keys.
Oh,